Hello everyone, I'm going to present our work titled A Read-Based Drone Control with Adaptive Arranging Update in Telexistence. Telexistence allows users to view and interact in remote environments rather than their current locations. Here we show that telexistence can be achieved by using an HMD and a UAV. First, the HMD records the user's head motion, which is translated to control signals to control the motion of the UAV in the remote environment. As the motion of the UAV is to mimic the motion of the head of the user, the images recorded by the camera on the UAV contain the designed view of the user. Then the images are transmitted back to the HMD to display to the user, so telexistence can be achieved, as the user can view the remote scene freely. This work tries to answer two questions in this telexistence system. First, how to freely control the drone with HMD in a limited space. Second, can HMD control achieve better performance than traditional solutions in some practical applications? There are two types of previous work in the literature. One is the rated control, where the position of the user maps to the velocity of the UAV. The key problem of the rated control is that it is hard for the user to perceive the arranging. This is a well-known self-centering problem. The other is body position to drone position control. A major flaw of it is that the flight range of the UAV is limited. To handle the aforementioned problems, we propose our mapping method. The left finger shows a 3D scene in the HMD, and the right one shows the corresponding 2D projection of the scene. Assuming that the user is standing at point A, the user's orientation is represented by the D vector, and C is the vector from the origin to the point A. Theta represents the angle between the vector C and the vector D. Based on this, the velocity of the pinch and roll is calculated as shown on the right finger. Then the velocity and the two dots of UAV is achieved. Notice that when the HMD is in the defined motion sphere, the UAV will stay still. The design is because that in a traditional read-based control system, when a user stays still at the origin and looks around, a slight position offset of the head is inevitable, which causes the motion of the UAV. To avoid this, within a predefined distance r from the origin, we only map the rotation of the HMD to that of the camera and keep the UAV hovering. The above mapping is just the traditional read-based control within a hovering mechanism. The self-centering problem is still there. As showing the finger, in some cases, the user may move to the perceptive origin and treat it as a real origin. Then, when the user moves to the current position, the real moving direction will be different from the designed moving direction. Therefore, we propose the AOU technique to eliminate this deviation. AOU, as you can find in the right finger, if the user steps back inside the motion sphere and stays still for more than 2 seconds, we set the current position of the HMD as a real origin, and the motion sphere moves to center at the new origin. In this way, the user could easily perceive the origin as it is updated by the user, so the self-centering problem can be solved. Next, we do two experiments to verify the performance of our method. In experiment 1, we designed a task where participants should control the drone to hit the golden balls that appear in a scene designed in Unity. This video shows the process of the experiment. Users need to use different technologies to control the UAV to follow the arrows to hit golden ball. We record the user's total flight distance, time, score, and the user's subjective workload, and finally compare them. This table shows the compared 6 technologies. Besides our method, we have tried different read-based and position-based solutions in these experiments. As you can see from the results in this table, we spent less time and distance and got better scores. This shows our method can control UAV more accurately and freely. The lower workload shows that our method is simpler for users than other HMD control methods. We designed another task which needs participants using virtual drones to reconstruct 3D models in a scene. 15 participants take part in this experiment and 6 techniques were compared. The participants need to reconstruct the model as completely as possible. This video shows the process of this task. The upper left corner is a real-time reconstructed model. The bottom left shows the interactive rendering of the reconstructed model in the RGB image shown in the HMD. The top right corner is the UAV's first view. The lower right corner is a view of the user being recorded during experiment. This table shows the completeness of the reconstructed 3D models of different methods. From the table, we can see that our method achieves the best reconstruction results, which shows that our method can achieve better and more accurate control, and the user can easily use this method to complete the 3D reconstruction task. In general, our method strategy improves the read-based control for the HMD-based telexistence. Our system still suffers from the latency caused by all the related components of our system. Furthermore, our system employs some predefined parameters which may influence users' experiments. In the future work, in order to reduce the delay, we will adopt a better compression transmission system algorithm. To predefine parameters, we would like to label some data and train a machine learning model to distinguish the meanings of users' motions. Finally, thanks for your attention.